So in the last lecture, we were talking about the generalized delta learning rule, and we looked at the backpropagation training algorithm, right? So how the generalized delta learning rule is used for training a multi-layered feed-forward network, right? So what is a generalized delta learning rule? What is a generalized delta learning rule? It is the delta learning rule which is applied to the hidden layer. So in a multi-layered feed-forward network, you have hidden layers. So the error signals need to be backpropagated to the previous layers, right? So that is where the delta learning rule, the generalized delta learning rule comes into picture. Okay. And we saw how it is used for training a multi-layered feed-forward network in the form of error backpropagation training algorithm. So just to recap quickly the error backpropagation training algorithm, because today what we are going to do is we are going to solve a problem on error backpropagation training algorithm. Okay, so we need to revise it quickly. This is how the block diagram of error backpropagation training algorithm looks like. Okay, so we were talking about this algorithm with respect to a single hidden layer. So there's a single hidden layer and so three layered architecture: input layer followed by hidden layer followed by the output layer. Okay, so some notations we had used to represent the input hidden and output layer weights, neurons as well as the weights. Okay, so Z was the input vector, Z was the input vector. Then we had the intermediate layer, that is Y. So Y is the output of the hidden layer and O is the output of the output layer. And then we had a set of weights connecting the input to the output, right? Input to the hidden, which were V. V weights were connecting the input to the hidden layer, and then W weights were connecting the hidden to the output layer, right? So using this, what we do, we there are two stages largely in the error backpropagation training algorithm, two phases or two stages for training. The first stage, what is the name of the first stage or the first phase? The feed forward recall phase, right? So you work in the forward direction, in the sense that you present the inputs and you keep on computing the outputs in the forward direction. So first of all, whatever is the training pattern you will provide to the network, right? You will give the training pattern to the network. Network will compute the outputs, okay, one by one, layer by layer. So outputs of the first hidden layer is computed, and then since we are assuming only a single hidden layer, then the outputs of the output layer are computed. Okay, once that is done, this is the first phase. The first phase is complete. Okay, so after this is done, you what do? You compute the error signals in the backward direction. So you have the second phase which goes in the backward direction, where you are computing the error signals, right? So error signals of, when you're computing, you make use of the delta learning rule, because error signals are nothing but the adjustment of the weights. Why do you need to compute error signals? You need to adjust the weight so that you get the correct output finally after training, right? So you can compute the error signals in the backward direction. So first, which are the first error signals that you compute? the error signals for the output layer. You first compute the error signals for the output layer, and then you compute the error signals for the hidden layer, right? So first you compute this delta O, which you see here, delta O. These are the error signals which you compute first. Then you compute delta Y. Why do you compute delta Y second? Because delta O are the error signals which will be used in the computation of delta Y, right? So delta O will be used for computing delta Y. So you need to compute delta O first. Delta O is the simple delta learning rule which you apply, which you extend to a layer of neurons, right? If you recollect, MCPTA. Delta O is MCPTA, delta learning rule. Delta learning rule for the output layer. Okay. And delta Y is going to use those error signals which you have computed earlier for the output layer, right? And find out the error. So you multiply with the f dash net, f dash y here in this case, and the w values. Okay. So that is how you complete the feedback phase. This is the feedback phase. Okay, feedback error propagation phase. Okay, and this is the algorithm which we also discussed last time. So this algorithm only we are going to follow, and we are going to compute the weights after one iteration for a given net. So what we are going to do today is we are going to use this algorithm, and we are going to train our network for one iteration or one epoch. Okay, so here everything is given, whatever we discussed just a while back, that is given mathematically here. So how are you going to compute the net values, right? Apply the activation function. So this phase that we see here, this phase is the first phase, the feed forward phase, where you are just computing the forward activations. So you give the input, compute hidden outputs, hidden layer outputs Y, right? And then you compute final layer. And the second phase that you have here is that you see here. This is the error calculation phase, where you are computing the error signals, right? So first set of errors is simply delta learning rule. Delta learning rules is what? D minus O times F dash net. What is the learning signal for delta learning rule? D minus O times F dash net. And F dash net is half 1 minus O square in case of bipolar continuous. If you recollect, are you able to recollect this? Half 1 minus O square is the derivative of that output, right? And multiplied by D minus O. This is the delta learning rule for the output layer. And using this error signal that you have computed, you're going to use this in the calculation for the hidden layer, right? This one. So delta Yj that you see is half 1 minus Y square. Now what is this? F dash Y, F dash Y. So it is always F dash Y, the output, F dash net or F, whatever it is, the output of that layer. So O is the output of the output layer, and Y is the output of the hidden layer, right? So derivative of that output, derivative of the output is half 1 minus Y square, because Y is the output of the hidden layer. Derivative of the output is half 1 minus Y square, because the activation function which is used, Y, that for computing Y, is nothing but bipolar continuous. Okay, multiplied by summation delta times W. Okay, so if you have a layered architecture here, so if these are the hidden layers, if these are the neurons, assume this is the hidden layer, this is the input layer, right? This is the input layer, and this is the output layer. N number of neurons, some number of neurons, some number of neurons. Okay, and there are connections everywhere. Right, everywhere there are connections. So if I'm talking about this particular term that we see here, okay, so if I consider neuron J, just let us consider neuron J. in the hidden layer. Okay, so if I'm considering neuron J in the hidden layer, if this is neuron J, then what is this term? This is nothing but you have error signals here, right? So summation of all the error signals which are connecting this neuron, jth neuron, to all the other output neurons. How many neurons are there in the output layer? There are k neurons, capital K neurons in the output layer. There are k neurons in the output layer, and each of these neurons are contributing an error signal. So that is, you have delta O1, delta O2, delta OK it is, right? So delta O1, delta O2, delta O3 up till delta OK. So there are k error signals for the output layer which are produced. Okay. Using these error signals, you have to compute the error signals for each of the hidden layer neurons. You have to compute the error signals for each of the hidden layer neurons. So when I talk about a particular neuron, jth neuron in the hidden layer, the small j that I see here, how will I compute this particular term? I'm talking about this term. Let me use another color. This term, right? How am I going to compute it? It will be all the error signals which are coming into it, right? So this one, I mean, whatever the weights are, these weights, whatever weights are connecting to it from the output layer, right? The green ones which I've shown. Okay. Multiplied by the error signals which are produced for each of the output neurons. Are you getting it? How this summation is computed? Delta OK, delta O1 times W, whatever this is, right? W1 it will be W1J, W1 W2J, W3J. Are you getting it? W1J, W2J, W3J, and WKJ finally. Whatever are the incoming weights which are connecting to the jth neuron, multiplied by the error signals which are contributed by those weights. Okay, all these you have to multiply and then sum them up. You will get this term, this green term. Okay, this term you have to multiply with f dash of y. Is this clear? So this particular term you are going to multiply with f dash of y. This is going to give you the error signal for the jth neuron. Likewise, you are going to compute the error signals for all the neurons in the hidden. Is this clear? Is this clear?
Yes, ma'am.
Okay. Once you are done with this, you simply update the weight. So you update the weights of the output layer, you update the weights of the hidden layer. Okay. And then you go ahead with the training procedure, which is usual. You give the second pattern, third pattern, fourth pattern, and so on, whatever patterns are there in your training set. And then you complete your cycle. Okay. You complete your iteration after all the patterns are presented once. You complete one training cycle or one epoch or one iteration, and then check for the error. If you have reduced the error considerably, you stop the training. Otherwise, you go for the next iteration. Fine. So this is the error backpropagation training algorithm. This exactly we are going to use for solving the problem. Okay. So let us go to the problem now. Okay. So this is the problem which is given to us. This is the kind of network we are looking at. And there is one input pattern which is presented, okay, which is 0, 1. So there are bias will be there everywhere. Okay, so there's one extra. Apart from this, there'll be one bias neuron everywhere. So what you see here, this one is the bias. This is one bias neuron, which is a fixed neuron. The bias values are given to be 1, 1, and 1. So the notations here slightly different. So whatever it is, the logic that eBPK follows, that you have to use it here. Okay, any label they can give here. Now they have changed in the problem, it is changed, it is X, Z, and Y. But the usual notation that we have seen in the algorithm is something else. Just remember the sequence, what you're going to do, how you're going to use the logic of eBPK to solve the problem. Okay. Only the names are changed here. So this is called X, this layer, input layer is called X, hidden layer is called Z here, and output layer is called Y here. Okay. So these are the weights. So V weights you have here, weights are however same. Okay. So V01 is V01 and V02, they are same. They are actually the bias inputs. So it's the same. This is actually what, if you want to figure this out, this is like this. There's a bias which is connecting here. Okay. And there is a bias one more here, which is connecting to this layer, to this neuron. Okay. There's a bias neuron here. There's a bias neuron here. In every layer, there is a bias neuron except for the output layer. Okay. So what is happening is this is connecting this. This is a fixed input one, which is actually connecting to Z1, and the value, that weight value is 0.1. The weight value is 0.1. And the same fixed neuron is connecting to Z2. The value is 0.3. The weight is 0.3. Okay. Similarly, for this particular bias, which is there, which is connecting from the hidden layer to the output neuron, the weight value is minus 0.4. So the weight of this connection is minus 0.4. Are you getting the architecture? Okay. Apart from this, the desired output is given to be 1, and you have to use bipolar sigma. Okay, for one epoch. So you have to train this for one epoch using eBPT. This architecture, whatever is given here, you have to train it for one epoch using eBPT. Okay, so that is the problem. Okay, so let us solve this problem. I'll share my screen again. Give me a minute. Right? Yeah. So usually I solve it using table. Here also I'm solving using table. You can use the equations and just solve it step by step. That is up to you. Okay. So we will divide it into two tables. First is the forward phase table and second is the backward phase table. Since the calculations are also, we are just going to follow the algorithm. The first table is the forward phase table. The second table is the backward phase table. Okay. So first of all, let us compute the forward phase. Now for the forward phase, what is given to you is X is the input. If you go back to the network, input is 0, 1, plus there's a bias connection. So I have added that bias here. So 0, 1, and 1. Similarly, the weights for the hidden layer are V and the weights for the output layer are W. Okay. So whatever weights are there, from here I have picked them up. So 2, 1, 2, 1, and this weight is 0.1, right? 2, 1.1 is the first weight vector, and the second weight vector is 1, 2.3, right? 1, are you getting it? 1, 2, this weight, this particular weight, and this weight. This weight is nothing but 0.3, which is given here. Is this architecture clear and how I'm getting the weight values? This is very important because if you just misplace the weights, then your calculations will go haywire, right? So you just see which weights are connecting to that neuron. So accordingly, you write the weight vectors. Is this clear to you? Because it's a weight matrix, right? It's a matrix of weights because there are two neurons, there are multiple neurons in the layer. It's not a single layer. It's not a single neuron, right? In that layer. So be careful while writing the weight vectors. Otherwise, you are bound to make mistakes. That is what I'm trying to point out. Okay. So once you do this, um, a table with the weights is complete. This is the V weight. Similarly, the W weights also I've copied here. So 0.42 and minus 0.4 is for the bias. Okay. Now what you need to do is you need to compute the forward activations. What do you do in the forward phase? You compute the activations, right? And apply the compute net and then apply the activation functions. Basically, that is what it is. So we will compute the net first. So first of all, we will compute net for this layer. So it is V times X, right? V times X. That is what you have to write in this column. So V times X. What is V times X? Can you tell me? What is the first? This vector, this multiplied by this. Tell me what is V1 times X1?
1.1.
1.1, right? Right. Similarly, V1, V2 times X1.
2.3.
Okay. Now, if you look here, go back. I'll just go back to the architecture. We are computing the net values for this layer now, right? We are at this layer. We are computing the net values for this layer. Now, one thing that you will note here is that there is one more neuron here. But this neuron is a dummy neuron. This neuron, I had mentioned earlier also, it is a dummy neuron. So what you're going to do is weights will be updated, but the output of this neuron is exactly equal to the input. It is fixed. It's a fixed input neuron. The output is exactly equal to the input. Similarly, this is in fact the input layer, so it is fine, but this is a hidden layer. So that is what I want to point out here. It is exactly equal to the input. Okay, we are not applying the activation function here. That is what I'm trying to say. So this output, so that the third value, net value, or whatever, whenever you apply the activation function, it's going to be 1 only. Z values will be 3 because there are 3 neurons, right? In the hidden layer, including the bias. Including the bias, there are three neurons, but the bias is a fixed output, fixed input, fixed output. Okay, so be careful about that. Rest all of the neurons, you apply the activation functions. So activation function for this particular example, it's mentioned it is bipolar sigmoid. So to use bipolar sigmoid. So since we are using bipolar sigmoid, so it is tan h x by 2. So simply this is x by 2. X is this, right? The net value. The argument to this function is the net value, this 1.1 and 2.3. So apply that activation function over it and tell me what is the value.
0.5005.
0.5005.
5.
Right. Similarly for this one,
0.8177.
88.
0.8177.
0.8177. Okay. So this is our Z vector now, the output of the hidden layer. Now we have computed this much, the output of this layer. Okay. Now using this, you have to compute this output is going to be the input for the final layer. Yes or no? this output vector that we have is going to be the input for the final layer, right? This is going as input to the final layer. So simply you need to compute the net for the final layer. Now, final layer in our case is having only one neuron. If there are multiple neurons, you will have those many net values, right? In this example, there is only one neuron which is given. So only one net value. Fine. So W vector is there with us. Simply, how are you going to compute the net? Simply W times Z, right? So in this case, there's only single neuron, W1 times Z, whatever you have got. So what is the output? What is the net value? This times this column, right? Minus, is it negative?
Yes, minus 0.03626.
Apart from Harsh, others are not solving. Please solve the problem. We have ISC on this, na? Problem solving on 8th of November. Okay, just to remind you. So, see, if you solve in the class, then there's an advantage, then that your Diwali vacation is not spoiled. Na? If you're not solving, then exam is there immediately after Diwali vacation. So see how you can manage your time, because you have to practice for this. I told you earlier also, you practice. If you're not practicing, your practice is not good enough, then it becomes difficult to solve in that stipulated time. Right? You can take the entire day and solve, but the exam is limited, right? So practice makes you faster in problem solving in this case. So see if you can just take my advice and work on it. Anyways, coming back to this problem, we have WZ, which we have computed, minus 0.0362. Now, finally, output of this layer has to be computed. So what is the output? The output Y is again activation function applied for this. Okay. So apply the activation function and tell me what is the output. It is tan h x by 2. Just put as argument to tan h this x by 2 minus 0.0362, whatever you put.
Minus 0.01812.
Minus 0.0181. Up to 4 decimals, you should keep this, huh? 0.0181 ना, 14 है ना आगे.
128 आया.
Okay, 128, fine. Up to 4 decimals or whatever weight calculations, whatever output calculations, keep it up to 4 decimals. Not more than that, not less than that. Okay. D minus Y. Next, why we are this D minus Y is not required. Okay. Later on when we update the weights, we use it. So these are the forward activations. Fine. So this phase is complete. This phase is complete. Forward activation phase is complete. We have computed the output. Okay. What we can do is, what I've mentioned in the next phase is we need to compute the cycle error also, because at the end of the cycle, we need to check for the error. So error is half d minus y square. So that you can compute and keep it there. Okay. So d minus half of d minus y the whole square. Okay. If it is a single neuron, since it's a single neuron, it is only d minus y the whole square. Otherwise, it will be summation half d minus y the whole square. If there are k neurons in the output, suppose there are 3 neurons in the output layer. So you will get 3 different error values, right? Squared error values. Sum them up together. That will be the error. Okay. So that is your first phase, feed forward phase. Now go for the backward phase, feedback phase, or the backward pass. It is also known as backward pass. The forward pass and the backward pass. This is called as the forward phase or forward pass, right? And this is the backward pass or phase. Anyways, coming back to this, what are you going to do in the backward phase? You are going to propagate the errors back, right? So first of all, you need to compute the errors. As we saw in the algorithm, the error formula for output layer is different, the hidden layer it is different. So first you need to compute which errors, output or hidden?
Output.
Output, because the hidden layer weights errors are going to depend on the output layer errors, right? So how do you compute the output layer errors? Okay, I will just write these old weights. These were the old weights. We need to update it at the end. Na? The new weights we need to compute. So I'm just writing this. These were the old weights, initial weights. And we will find the new weights once we compute the error signals, because it is CRX eta times error signal times the input. Do you recollect? That is what we have written here. V plus, this is the weight update, right? V is equal to V new is equal to V old plus eta times delta Z times X. X is the input to the hidden layer, right? In our network, X is the input to the hidden layer. Similarly, for W, it is eta times delta Y, the error signals for the output layer, times Z. Z is the input to the output layer. Right? Are you getting it? This is with respect to this diagram, whatever is given in this problem, right? Eta times delta OK, delta O, delta O's. Delta O in this case, we are calling it as delta Y, because the output is not O, it is Y in this terminology. All the delta Y's times the input to this layer. The input to this layer is nothing but Z, right? Z, na? The input to the output layer is Z, na? The same rule, only thing is the notations, the labels will keep on changing depending on what alphabets are being used. But you should just remember the logic. That is what I'm trying to say. Don't get confused. Just remember the logic. It is CRX. X is where X is the input to that particular neuron. You recollect this very first generalized learning equation? CRX. R is a learning signal. C is the learning constant. X is the input, right? So is this clear? Are these weight update equations clear now that you need to follow? Okay. So let us just first compute the error signals for the output layer. What are the error signals for the output layer? How many error signals you tell me will be there for the output layer? If I go back to the network, how many error signals will you have for the output layer?
1.
1. Why 1? Why did you say 1?
एक ही न्यूरॉन है इसमें.
Because there is one neuron. Very good. So how many neurons are there? Those many error signals you will have. Okay. You have to. How are you going to compute this? Normal delta learning rule, the usual delta learning rule that we have for the output layer, right? So that is d minus o times f dash net. वो rule है ना अपना delta learning rule. So for the output layer, it is very simple. D minus output of this layer. Output of this layer is y. Output of the output layer is y, na, in this case. So d minus y times f dash y. Right? So now how you are going to compute this? Just multiply d minus o. First of all, you compute d minus o and you multiply that with f dash. So that f dash y is nothing but half 1 minus o square. Half 1 minus y square. So I will write it as into half 1 minus y squared. Correct? D minus y into half 1 minus y square. This is clear? Anyways. Yeah. So tell me, apply this formula d minus y into half 1 minus y square. I will write the weights for this also. What value you are getting? Point
0.494.
0.494. Are you sure? Half. D is 1, huh? D is given to be 1.
Output minus 0.0181.
I am getting something else. 0.5089 I am getting. No? Only one person is solving, so I don't know whether. Okay, D minus O. Let me check. D is 1.
हाँ आपका करेक्ट है वो मेरा एक डेसिमल में मिस्टेक
0.5089, na?
हाँ हाँ
So 0.5089 is delta y. Okay. Error signal for output layer is computed. Done. Now we need to compute the error signal for the input layer, for the hidden layer using this, using the output layer error signal, right? So for the first neuron, if I go back to the diagram, first of all, what is the formula? The formula is f dash in f dash of, I will write this as f dash of z, okay, times summation of delta y times w, right? Yes or no? The weights which are connecting, if I go back to the diagram, let me go back to the diagram. Delta y I computed. There is one error signal for this neuron. I've computed delta y. Now what I need to do? that delta y I need to multiply by this weight. Okay, it's going to give me the error signal for this neuron. Okay, multiplied by f dash net, f dash y, f dash z, whatever it is. Yes or no? Okay, all the incoming, I mean all the weights which are connecting from the output layer to this particular neuron I'm going to look at, but there's only one weight which is connecting to this neuron, because there's only one neuron na, in the output layer. The output layer in our case is having only one neuron, so that is why that summation will not come, only that product will come. Are you getting this? Whatever I was talking about the jth neuron, if you remember, either. Do you recollect? ये jth न्यूरॉन है, इसका एरर सिग्नल निकालना है. You have to find out this error signal. So that will be all the error signals which are incoming to this from each of the outputs of the from each of the neurons of the output layer, multiplied by the corresponding weights and the summation of that. Fine. And then this term, that was this term, summation, whatever we had written, summation delta OKW. This term multiplied by f dash of this, output of this. That is the error signal for that neuron, J. Okay. Now what is the problem? The problem is not a problem as such, but there's only one neuron in the output layer. So there's only one incoming weight. So that error signal will, that term, that summation will simply reduce to a product of that weight with that error signal, of this weight with the error signal, green error signal, whatever it is sending. Is this clear? Can you relate in this context? For this neuron, there's only one weight which is incoming from the output layer. So multiply it with the error signal for that output layer, for that neuron. Okay. Similarly for this neuron. Okay. So delta Z1 and delta Z2. Okay. Tell me what are the values?
0.1018 or 0.0832.
Point 0.07. It is simply this signal multiplied by the weight which is connecting. Multiplied by f dash net, f dash of z, f dash of z. Use this equation. This is the equation. f dash z है, क्या मिला आपको? 0.0763 I am getting.
एफ डैश ऑफ जेड क्या लिया आपने? मुझे वो नहीं समझा. लाइक वो ऊपर एक
f
जेड
dash
आया था.
f dash of z, no? F dash of z is this, no? Okay, z I have not written you. Sorry. These values, no? Z.
तो उसका वापस 10h/2 कर देने का.
नहीं, उसका वापस नहीं. ये वैल्यूज है, इसका हाफ 1 माइनस ओ स्क्वायर, हाफ 1 माइनस z स्क्वायर.
ओके ओके ओके.
This is the equation. Half 1 minus that z square times that, na, error signal. You should get 0.0763.
Yes, ma'am.
Okay. Now what you need to do is you need to actually update the weights. Okay, error signals are done. You are going to update the weights. How will you update the weights? This equation which is given here, you have to follow. Eta times eta is 1 given to you. Okay. So delta z. So if you are updating the hidden layer weights, it is delta z times x. Okay, x this vector. Okay. So multiply the delta z. Delta z is given to you. You have just computed.
मैम यहाँ पे डेल्टा ऑफ बायस हमने फाइंड नहीं किया.
नहीं, बायस का जो आउटपुट है इट इज फिक्स ना, इट इज 1 ओनली. तो
उसका वेट तो
वो 0
अपडेट.
वेट है, उसका वेट अपडेट होगा ना.
ओके.
First is 2. Eta times eta is 1, so ignore that. Delta z times x. How are you going to multiply them? What is v1? V1 is 2.
1.0763. नेक्स्ट वाला शायद.
The next one, na?
हाँ.
1.0763, correct. What about the bias now? Bias weight will update.
0.1763.
What did you say? 0.1763?
हाँ.
हाँ, बराबर. Okay, so update it, but remember that is what? It is a fixed output, so that becomes 0. 0.1763. Correct, na, Harsh?
यस मैम, वो बायस उससे मल्टीप्लाई करके ऐड
हाँ
किया.
हाँ हाँ, बराबर. Next, what else is there? The second one, second also along the same lines.
वन 2.0168 0.3168.
1, 2.01,
68.
and
0.3168.
barabar. Okay, so this is V1. Similarly, W1. W1 will be eta times delta y times z. Delta y is a single value that you have. So simply that multiplied by the input vector z. Input vector for this layer, that is the z, this one, z is this.
Point 4, 0.7089 or 0.1089.
0.4
हाँ क्योंकि उस अच्छा सॉरी जेड
डेल्टा
है हाँ
w निकाल, डेल्टा w ओल्ड वेट्स में ऐड करो. eta times
0.6547
हाँ 0.6547, 0.6547 6162 and finally it is 0.9. And also compute the cycle error, half d minus o the whole square. It comes out to be 0.5183. I'll write it down. 0.5183. So this is one complete iteration of backpropagation train. Okay. Just for practice, what we will do is in the next lecture, I will take a complicated network where there will be two neurons in the output layer. Okay. And we will solve it using the step-by-step fashion, maybe. Okay. So let us stop for today. We'll continue one more example we will see in the next lecture.